So we'll have this start of the next set of courses on information theory by Jaikumar Radhakrishnan. So he's from ICTS itself. Yeah. So yeah.
Thank you for coming. My name is Jaikumar Radhakrishnan, and I'm a theoretical computer scientist. So I was asked more than 1.5 years ago to perhaps talk about information theory at the school. At the time, I thought I would learn some physics and perhaps combine what I know with what I learn and tell you something that would be perhaps more meaningful to you. Somehow I have not got around to doing it. So I'll largely stay within my comfort zone. Okay, so I'll tell you how information theory is studied in perhaps areas such as communication engineering, and notions like entropy will show up in the discussion, and I will leave it to you to relate it to your ideas of entropy. And if you have something to tell me at the end of the course or during the course, I'll be very happy to learn. Okay. So I have made some notes, and they are available at this website. I probably will notice errors as we go along. I'll correct them, and by the evening, it will be on the website of the Bangalore school. Good. So today we'll talk about the problem of information transmission. So this is the title. The Mathematical Theory of Communication was a paper that Shannon wrote in 1948. And one of the problems was the problem of information transmission. So how did this problem get modeled? And how did we finally arrive at the notion of entropy? Okay. So that will be the topic of the discussion today. So what we have is a source. What's a source? A source has some symbols, x1, x2, xk, and corresponding probabilities. Okay. So you can imagine this to be an experiment that has been performed. And whenever you perform the experiment, the outcomes can be x1 to xk. But the experiment, as your experiments, are not deterministic. Each time you do it, you get a different result. But there is a certain probability with which these outcomes are received. Okay. Now, the set of outcomes also be denoted by x, and that is and sometimes we call this the alphabet. Okay. So there is a problem in the day-to-day use of the language. We have somehow in India started referring to letters A, B, C as alphabets. So I think that's a sign of illiteracy. English language has only one alphabet, which has 26 letters. Okay. So for our discussion today, we should just say that these could be letters, symbols, characters, etc. Don't call them alphabets because I'll get confused. Alphabet is the set. Yeah. Okay. So when your experiment is a coin toss, then your alphabet is just two possibilities, 0 and 1. And if it is a fair coin, then 0 will appear with probability half, and 1 will appear with probability half. Okay? So this is a source, and it spits out one of these symbols with the corresponding probability. Now, what is the problem of information transmission? There are two parties, Alice and Bob. And Alice performs this experiment and receives an outcome. And she needs to transmit this to Bob. And Bob must then decode it and obtain the message again. Okay. So in the standard model of communication, you have an encoder to which you send in the message, and then what you get out is it's a code word. Yeah? So message you should regard as one of these symbols. You feed it to the encoder, it encodes it into bits of zeros and ones, strings or words of zeros and ones, and then it is passed through a channel. And then we come into Bob's territory. Maybe I should write Bob here. And Bob decodes it, and yeah. And this is called the received word. So some word is sent, some word is received, and then you do a decoding and you get the output message. And the goal would be to ensure that the message that was intended to be sent by Alice is, in fact, the message that is decoded by Bob. Yeah? Now, sometimes this channel here will play some tricks. That is, when you send it, when you feed something into the channel, what it puts out is not always the same symbol. Yeah? Because the channel itself is probabilistic. Okay? In which case, this process of encoding will have to be done carefully. Actually, this encoder and decoder will have to work together so that with high probability, the message that comes out is the intended message. Okay? Today, we will be working with channels which make no error at all. Okay? And actually, we will only be interested in sending zeros and ones into the channel, and the channel will come out, will send things out as zeros and ones without errors. Okay? But then what is the problem? The problem is we would like to send as few bits as possible. Okay? So the goal is minimize So, for example, this could be your alphabet, exclamation mark CELMOW. And the encoding that I'm using here is whenever I wish to send exclamation mark, I will send 000. Whenever I want to send C, I will send 001, and so on. Okay. And now, suppose Bob receives this message. Yeah. Then Bob decodes it. And how does he decode it? Well, perhaps because all messages have the same number of bits here, he knows that, sorry, what did I do? And so on, yeah? And if I copied it correctly, did you decode this? And what did you get? Welcome, yeah. So that was the message, I am Alice, you are Bob, yeah? And You heard, right? Sorry? There is no exclamation mark here. Oh, in the message, I forgot. Okay, sorry, yes. Okay. Oh, I see, okay. Yeah. It was intended, so maybe I'll. Yeah, okay. All right. Yeah. I'll correct that in the notes. Yeah, okay. All right. So, I've told you, yeah. So our alphabet is 0, 1. And when I write sequences of letters from this alphabet, these I call words. Okay. And if I have two words, sorry, yeah, X and Y, then I write XY. You should think of this as the concatenation of the two words. Okay. So suppose X was 0, 1 and Y was 1, 1, 0, then XY will be 0, 1 followed by 1, 1, 0. Yeah. That's what we mean by XY. So this is concatenation. And we say that Y is a prefix of X if Y appears in the beginning of X. So 1, 0 is a prefix of 1, 1, 1. Sorry. 1, 0, 1. Now, it will turn out, it will be convenient. You see, the point is we are going to take a message, and the message might involve multiple letters from the alphabet. And we are going to be encoding them. We will come up with a table like this, but here all the code words were of the same length. Okay? When we solve this problem, we will need to design a code in which all code words will not be of the same length. Okay? Yeah. And in that case, when does one code word end and the next code word start will need to be determined by Bob. Okay? And if the code, the encoding is prefix free, meaning, so we will have x1, x2 to xk, and then the corresponding words will be w1, w2, wk. These will be 0, 1 words. And these are symbols from the alphabet. So when we need to transmit a message which consists of many xi's, we will just take the corresponding words and concatenate them and send them. On receiving this, Bob now needs to cut it up to understand what is the first symbol that was sent, what is the second symbol that was sent, and so on. Okay. Now, if we know that the code words here that are being used are prefix free, okay, so as he starts reading, he would immediately know when the first letter is over. Is this clear? Suppose one of the symbols is encoded as 1, 0, and the other symbol is encoded, say, let's say this is the code word for A, and this is the code word for B. And he has received 1, 0. More letters are coming. Can he be sure that it is A when he receives 1, 0? No, because maybe more letters can come and then it will become D. But suppose the words that he uses here are prefix free. That is, none of them is a prefix of another. The moment he sees one of the words here, he will know that it is the corresponding letter. Is this clear? Yeah? No, they are not necessarily of, if they are all of the same length, he could just wait for, say, in that case, 3 letters, then he knows it is A. Next 3 letters, it is something, and so on. But suppose they are of different lengths. That is, A has been encoded by 2 symbols, but B has been encoded with 4 symbols. Still, if these words here are such that no word is a prefix of another, then the moment he starts scanning and keeps looking whether this appears in the table, what he has received, the moment it appears in the table, he knows that the corresponding letter was intended to be sent. Yeah? Because there cannot be an ambiguity, because if there was a different letter, then that word would have been different. And this word cannot be in the beginning of that word, okay, because they are prefix free. So we will like to design a code which is prefix free so that Bob is able to decode on the fly. Okay, so this is a sort of technical restriction that I'm imposing on the problem. And let me then write down what we are trying to do. We would like to minimize. Okay, so suppose, yeah. So, question. X's are some abstract symbols which are outcomes of some experiment, which is W's. Yeah, good. So these are the symbols which are produced by the experiment. These are the words that need to be fed into the channel. Okay. Yeah. Question? Yeah. Yeah. Yeah, because he saw from the beginning 1011 has come and it is B. And then he starts again. He kind of comes back and starts again. Things will become easier than it appears very soon. Yeah. This is not prefix free. The design. So Alice and Bob will sit together and design an encoding for x1 to xk. Okay? And they will ensure that the words that they are using are prefix free. Okay? So this is an engineering requirement on this so that we can decode on the fly. No word in the right column is a prefix of another word in the right column. They are not just different from each other, that nobody appears in the beginning of another. Okay. Question? Yeah. So, yeah, what's a prefix? So, suppose this is your word. 1 is a prefix of this word. 10 is a prefix of this word. 101 is a prefix of this word. 1011 is a prefix of this word, and so on. Okay? When we say that a particular encoding is prefix free, we mean that no word here should appear in the initial part of another word here. Okay? That is the requirement. Okay. Yeah. If you put this as a word, these words are not allowed. Okay? Yeah. So now, the problem that we are trying to solve is the following. We want to minimize, yeah, so when I write 0, 1 star, I mean the set of all strings with zeros and ones. Yeah, so all such strings of all possible lengths. Yeah, that is 0, 1 star. And our goal, what's an encoding? Encoding is something which takes a symbol from the input alphabet and assigns to it a word. But we want to minimize over F such that F is prefix free. Yeah? And what are we trying to minimize? We want to minimize the expected cost of transmission. So what is the expected cost of transmission? Summation over all x belonging to our alphabet of the probability of that symbol times the length of the encoding. So when I write 2 bars around f of x or any word, yeah, so sorry. This is, what is this? Yeah. Because its length is 3. Okay, that's what I mean. Okay. So now, suppose Alice and Bob decide to use this function f for encoding their symbols. Okay. And they ensure that it is prefix free. Then, if this scheme is used for transmitting symbols that are produced by this source, per experiment, what will be the cost? How many bits will they have to send through this channel per experiment? Okay. On an average, this will be the expected number because the probability that the symbol x shows up is p of x. And when x shows up, they end up transmitting these many bits. Is this clear? Nothing is happening. Yeah. Okay. Now, yeah, so this is the problem that we will study for some time. This prefix free, first of all, this is a discrete sort of an optimization problem, yeah, under this prefix free restriction. And this prefix free restriction makes things a little awkward, but very soon you will see that yeah, things can still be managed. Okay. So this, where did I write? Yeah, this 0, 1 star, I would actually like you to imagine as an infinite tree. So this node corresponds to the empty string. This node corresponds to the string 0, 1. 0 first, then 1. Okay. 0, 1, 0. Okay. And this goes on. So instead of thinking of it as this abstract set 0, 1 star, I think of it as nodes in this infinite tree. Okay. Now, what does prefix free mean in the language of this tree? Yeah. So suppose there is a word. Where is that word? 1, 0. 1, 0, 1, 0. Yeah. Now, if it is 1, 0, now where is 1, 0, 1, 1? 1, 0, 1, 1. Yeah. Yeah, so when are they not prefix free? When is W1, so when is W1 a prefix of W2? Okay, so can I call it W1 is a parent or an ancestor of W2? Yeah, in the language of family trees, Yeah, yeah. So, good. So this is a convenient way of visualizing prefix free. That means Alice and Bob now need to, the moment they choose this as a code word, this entire subtree gets killed off. Very good, killed off. Yeah, like violent words. Yeah. So yeah, yeah. Yeah. So yeah, so it gets killed off. Yeah, yeah. And so they need to find some uh, some words with some nodes on this tree, so that it is none of them is an ancestor of another. Yeah. Okay. So suppose F, which is a map from the alphabet to 0, 1 star, is prefix free, then so suppose somebody gives you a prefix free encoding. Yeah. And now you look at the lengths of the code words that they are using. And you do 2 to the power minus the lengths. And then this number will be less than or equal to 1. Okay. And a proof. Somebody said it already. So when I asked what is the definition of prefix free in the tree, they said, you know, one should not appear in the same path or trajectory. What was the word you used? Trajectory, yeah. Now, we have had a whole week of walking randomly in the graph. Yeah. So suppose you took a random walk from the root down. What is the probability that you will hit the code word corresponding to X? Suppose you have a code word at distance D from the root, and you took a random walk, each time branching left or right with probability half. What is the probability that your trajectory will pass through this if it has distance D from the root? Minus D. Now imagine a random walk which started at the root, an infinite random walk which went down. What do we know? Because the encoding is prefix free, when you pass through one code word, that very trajectory cannot pass through another code word. Because no two code words appear on the same trajectory. That is exactly what you said. So these are all disjoint events. So their probability can add up to at most 1. Sorry, is this okay? Yeah. So yeah. Okay, I'm not writing everything down. Sorry, if there is a question or you would like me to explain this again, I'm happy to do that. This is the probability that your random walk passed through the node corresponding to the symbol X. Okay, and these events are disjoint events because on no trajectory, 2 of them lie. Okay, and since they are disjoint events, their probabilities can add up to at most 1. Is this okay so far? Yeah. Now, it turns out that this inequality also has a converse. So this is more or less a necessary and sufficient condition for prefix-free encoding. Okay, so let me explain. So suppose L Yeah, so this is, let's see. Suppose somebody specifies some numbers, yeah? Instead of telling me the words, they say that for x1, I want a code word with 5 symbols. For x2, they don't tell you exactly what code word is to be used. For x1, they tell you that the length of the symbol, length of the encoding should be 5. L for length. For x2, 7. For x3, 2. 15. They gave you such numbers. And they asked you, can you produce a prefix-free encoding where x1, where w1 has length 5, w2 has length 7. When can you ensure? Well, these numbers better satisfy this inequality. Yeah, because if you happen to produce such an encoding, then this inequality will be true. But the converse is also true. That is, if these numbers satisfy this inequality, then it is always possible to arrange code words at various heights specified by L, so that they are prefix-free. Okay. Now, so this part again, I will let you prove. It is a little bit of combinatorics that you will have to do. Yeah. So. Sorry, yeah, is it okay? Is my claim clear? Yeah. So there are two parts. This inequality must hold for whenever you have a prefix-free encoding, and if you have been specified some lengths, then you will find a prefix-free encoding with those specified lengths, as long as those lengths satisfy this inequality. Okay. So we had this theorem, we had this problem to minimize. And here there was this, we can now change that to saying that I want to minimize sorry. Yeah, so this seems to be slightly better. Here, we had to imagine what sort of prefix-free encoding we want to get. Now everything is about numbers. To each of these symbols of your alphabet, you have to assign a number. A non-negative integer, so that those non-negative integers satisfy this constraint. Under this constraint, you want to minimize this. That is the problem of information transmission. Is this okay? Yeah, yeah, everything okay. Yeah. Now, unfortunately, this is still not something that we can immediately write a formula for. Yeah, I will have something to say about this problem. But anyway, the optimum of this I call T of X. Yeah, so X is a source. X is a source where you have been, where symbols have been specified. There are k symbols and k probabilities. For that source, there is a minimum transmission cost. This is called the transmission cost. What is the minimum transmission cost? That is this problem. Yeah. What is the minimum transmission cost for this? And that problem we saw was equivalent to this problem because of these two mathematical observations. Is that okay? Yeah. But the only awkward thing here is this integer. Yeah. If only this was, we were allowed arbitrary real numbers, yeah, then maybe we would be able to use whatever method of Lagrange multipliers or something and write the optimum for this. Okay. So let me write down the problem. So I'm going to copy this here, minimize summation x belonging to x, px. I'm putting a little tilde on top of this. Now I'm allowed non-negative reals, yeah, and subject to so this is a relaxation of this problem. Relaxation means the constraints have been relaxed. In what sense? We are now allowing real numbers. Previously, we were very rigid. We wanted only integer lengths. Now we are allowed real numbers. And we have this problem. Okay. Now, what is the optimum of this problem? Okay. Yeah. So let me temporarily call this T prime of x, or maybe just to be consistent with everything, T tilde of x. Okay. T of x, rigid problem. T tilde of x, relaxed problem. Okay. Yeah. Now, so let me write L tilde of x. I'm proposing a solution to this problem. Okay. I'm saying take L tilde of little x to be log of 1 over p of x. What is p of x? A source has been given to us. The little x has a corresponding probability. Take the reciprocal of that probability, take its log to the base 2. Okay. And define that to be L tilde of x. And let us compute what we get here. Here, does it satisfy this constraint? What is 2 to the power minus L tilde of x? 2 to the power minus log of 1 over p of x, summed over p of x. 1, this inequality is satisfied actually with equality. Yeah. So we are safe. Let us compute the objective. Yeah. So if we choose this L tilde of x to be these numbers, then T tilde of x, the objective that we get is this. And we know that this quantity, the optimum, can only be better than this. Because I have given you one solution which achieves this. The best solution for this problem can only be smaller than this. Okay. Now it turns out that actually this is the optimum. There is no better solution. Okay, and how do we prove that? So, claim. So this in information theory is called h of x So if you have a source or a random variable x, which takes k values with some k probabilities, and you compute this number, yeah, that number is called the Shannon entropy of x. Okay, and my claim is that this problem, which is a slight relaxation of the actual problem we wanted to solve, is actually the optimum of this problem, is in fact the Shannon entropy. Okay, and why? So suppose L tilde prime, yeah, is a prefix-free encode, sorry, satisfies so take any solution, L prime, L tilde prime, and it satisfies this inequality because you are only minimizing under this constraint. Now, what is the objective that this will achieve? Summation over x belonging to x, p of x, L tilde prime of x, and we want to claim that this is always greater than summation over x belonging to script x, p of x log we want to verify this because once we do this, we are done. Is that clear? We have got one solution which achieves entropy, and we want to say that give me any other solution, what it will achieve will always be greater than what we achieved. That means this is the best solution, or this is at least one best solution. Yeah. Okay, so just rearrange this. So what do we need to show? Yeah, so we want to show that summation over x belonging to x, px log, yeah, so I'm yeah. Oh, sorry, which is the line? So I've crossed the line. Yeah, okay. Yeah. So we have to show summation over x, px log, yeah, my logs are always to the base 2. Yeah. Yeah. I want to show that this is greater than or equal to 0. Yeah. Now, log, sorry, what do I, less than or equal to 0? Is that okay? Let me just explain. I take this to this side, I get 0 on the left, 0 greater than or equal to something, and there will be a minus sign here that will become 2 to the power minus L tilde of x. That's what I've written there. Yes. So now, a log is a concave function. Yes. So this quantity is less than log summation over x. So this looks like expectation of the logs is less than log of the expectation because it's a concave function. Sorry, too many logs. This is less than this because log is a concave function. And summation 2 to the power minus Lx is less than 1. Yeah. So this quantity is less than 1. That means log of that quantity is less than 0, which is what we wanted to do. Is this okay? Yeah. So what have we achieved? We have shown that the problem that Alice and Bob wanted to solve was this. If only they had allowed real numbers instead of integers, then they would be left with a problem whose optimum is actually the Shannon entropy of x, the entropy function. Okay. But what about the real problem, the integer problem that Alice and Bob wanted to solve? So let me just erase this. So how did we come up with this solution? We did 1 over p of x and took the log of that. Now this in general need not be an integer. It can be a real number. Yeah. Now how do we make, what they would really like is something that's an integer. So why not define L of x to be take every number and round it up. Yeah. Now if you take every number that was there before and round it up, what happens to 2 to the power minus n? This number only becomes smaller. So if the original inequality was satisfied, it will continue to be satisfied. Yeah. And by this part, we know that there will be a prefix-free encoding. So P of x, the actual transmission cost of x, is definitely less than what this provides. So this is summation over x, P of x, log to the base 2 of sorry. Now, when you round a number up, by how much can it increase? Yeah, it cannot increase by 1. So this number and the corresponding number here are off by at most 1. Yeah. And anyway, you're taking an average. So if you take any number and increase it by 1, what can happen to their average? It can also increase by at most 1. So where was I writing? Yeah, here. So this quantity so what do we know about the transmission cost? The transmission cost is always at least the entropy. Why? Even the relaxed problem's optimum is entropy. So the unrelaxed integer problem's optimum cannot be less than entropy. Yeah. And we have demonstrated here that the relaxed problem, sorry, the integer problem can have a value at most entropy plus 1. So let me write this down. So this is the main theorem for us. let me pause for a minute. Yeah. How did all this come about? Yeah. Suddenly entropy seems to have popped up into what looked like a very rigid problem of design of codes. Yeah. So it turned out that we imposed this restriction that the codes, the encoding that we do should be prefix free. Okay. This encoding, this prefix free condition had an equivalent mathematical formulation. Because of this, we could translate this English into an inequality. Okay, that is the message of these two columns here. Yeah. Yeah. And once we did this, there are many ways to solve this. I have just done something here. I've shown you a solution which achieves entropy, and I have proved here and there that you cannot beat entropy. Okay. On the other hand, the real valued solution that we obtained here can be rounded up to obtain an integer valued solution. Take this integer valued solution and pass it through this. It will give you a prefix free encoding where the length of the code words will be exactly this. In that case, the cost of transmission will be px log 1 over px rounded up, and that contributes at most 1 to this. And as a result, we are entitled to write this theorem. Okay, so this is called with variable length encoding. Different symbols of the alphabet will receive different lengths. Yeah. And somehow, what is happening? If your probability is very small, very large, suppose your probability is very large. If your probability is very large, you will be given small code words. Yeah. If your probability is very small, anyway, you are going to appear very rarely. I don't mind sending more bits. So if P of x is small, this number becomes large. Now the log is because of the branching nature of this tree. Okay, that's why there is a log. Bigger number, bigger probability, smaller code words, smaller probability, bigger, longer code words. Okay. Yeah, so I left this as an exercise, how to do this. Yeah, yeah, but that is one way. Among them, find the longest, chop off the tree, and then do this. There are also methods by which these numbers can actually be given one at a time. So you are not even told which one is the longest, but you are only promised that they will satisfy this inequality. Still, you can kind of arrange the code words on this tree, but keep this tree in mind. Okay. When you try that exercise, yeah, as Sanjib said, find the longest string, go there and chop off its. Yes. And then look at the next longest, it could be of the same length. Then you give it this. The next longest could be slightly smaller. The next longest could, and so on. And you will never get stuck. Yeah, you will never run out of places to put something. You will have to check that. This inequality does that. So yes, there is something to be done in this exercise. That's why, yeah. But you will do it. Yeah. Is that okay? Yeah. So yeah. So please ask. Are we okay so far? Yeah. Very good. Sorry, I have half an hour more. Yeah. Good. Let's see. We'll see. So, of course, it's not always better. Yeah, let's see. Yeah. Let's. suppose X so it was a fair coin. It took two values, 0 and 1, each with probability half. Yeah. Then what would the table look like? Well, for 0, you will have to probably encode it with 0, and you encode 1 with 1, and yeah, this is the symbol, and this is the encoding or the code word corresponding to this. And then T of X, under this encoding, what is the expected transmission cost? If you use this encoding, with probability half, you'll send 1 bit. With probability half, you'll again send 1 bit. 1. And what is H of X? Yeah, so log of 1 over half, log 2, my logs are to the base 2. So it is half times 1 plus half times 1. So H of X is also 1. Okay, so in this case, actually we have equality here. Yeah, but suppose it was not a fair coin. What do you think is the best encoding? Well, you will have to differentiate between 0 and 1. Sorry, so let's build a tree. This is the empty string. Where do you think you should put 0? Well, 0 has small probability and 1 has probability 3/4. So maybe we put 1 here, yeah? We keep it near the root, yeah? And 0 far away from the root. But you know, we might as well put the 0 here because that will only minimize the transmission. And again, T of X in this case is, if this is the code word for 1, this is the code word for 0, what is T of X? 1. But the entropy of this X is 1/4 log 4 plus 3/4 log, yes, and and if I had put, yeah, so let me call this on the other hand, if it was a 1/3, 2/3, I'll explain what I'm doing here, then H of X comes out to be, sorry, I made a mistake already. Not that these numbers are important, but just. Suppose P is a number between 0 and 1, and the probability, it's a coin, and it comes up heads with probability P and comes up tail, or sorry, tail with probability P, head with probability 1 minus P. Okay. then we can again compute the formula for the entropy, and it will turn out that the picture looks like this. And it is maximum at half. Okay. However, if the transmission cost in all cases is 1. Okay. So we have this strange situation. I was trying to tell you that entropy somehow is related to information. Yeah. And I took a very practical engineer's view. What is information? Actually, information is some philosophical object. I don't even care. Okay. I am an engineer. Yeah. So, but I will say information is the amount of cost that I need, amount of transmission I need in order to convey it. Without defining information, I just want to say how much effort does it take to convey something in bits. And traveling along that idea, I got a pretty good theorem. Okay. But this theorem, unfortunately, in some cases, as Sanjib pointed out, is not very satisfactory, because the transmission cost is always 1, but entropy is taking all kinds of funny values. Yeah. Is there some sense to the entropy taking all these values? Okay. And that is what I want to explain. So there is a way of thinking about information and transmission, so that the fact that when you take 1/4 here, then this number is only 0.811. And when you take 1/3 here, the value is, 0.919. Yeah. What is that? Why is it 0.811 here and 0.91? What is it? 0.919 here. Is there any sense to this from an engineering point of view? And I will tell you now. Okay. Is that clear? Yeah. So good. We know something here, but what is the meaning of all this? So I have demonstrated the difficulty we have in accepting entropy as this formula for information, because there is some discrepancy here. Okay. I would like to think about information transmission in a slightly different way, and then this discrepancy will go away. And this slightly different way is what I'm trying to explain now. Okay. So there is a source X, and these are IID samples from X. Okay. So I take N. So Alice performs N experiments. Yeah, N experiments. And first time she gets an outcome. Next time she gets another outcome. These many outcomes. And suppose X itself was a source like this, which had these outcomes. These outcomes now, they live in a set. How big is the set? What are the number of possible outcomes? If all these probabilities are non-zero, how many possible outcomes are there? If you make one experiment, there are K. If you make 2 experiments, how many possible outcomes are there? K squared. And if you perform N experiments, K power N. So these outcomes, the set of outcomes, live in a set here, yeah, the set of outcomes, set of possible outcomes. And the cardinality of this set is A power n. Yeah. Now, all these outcomes don't have the same probability. For example, maybe one of these symbols has probability 0. Yeah, maybe this was the symbol exclamation mark. Okay, and it had probability 0 because nobody ever uses an exclamation mark. So then all these sequences need not be encoded by Alice because, you know, exclamation mark is never going to come. Okay, so there are some things with 0 probability, some outcomes here, x1 to xn, yeah, which don't happen at all. Okay. So we could focus on this. But here again, all outcomes don't have the same probability. Yeah, some outcomes have high probability, some outcomes have low probability. For example, in this experiment, what is the probability of 0, 0, 1? If I perform the experiment 3 times, what is the probability that I would get 0, 0, 1? Yeah, so 1 by 4 times 1 by 4 times 3 by 4. So depending on the mix of various, n is very large, k is very small. Okay, perform this experiment many times. Then depending on the mix of symbols here, the empirical distribution here, your probability will be different. So not all these sequences have the same probability. Okay. So Alice and Bob say, you know, they fix a small delta. So now they are willing to tolerate error of delta. And they say, among these sequences, let us just encode enough so that their probability, so this is a set A, so that the probability of A is at least 1 minus delta. Sorry, let me explain. Alice and Bob imagine that they have to perform this experiment a large number of times. And then they say this large number of times would correspond to a large number of possible outcomes. Among these outcomes, let us focus on enough of them so that our transmission succeeds with probability 1 minus delta. Delta is the error parameter. We are ready to tolerate an error of delta. Yeah. And then to each of these outcomes, they will assign a code word. Okay. So what will be the length of transmission? If there are these many words, possible outcomes here, yeah? And so the cardinality of this set is A, yeah? These many outcomes. And to each of them, they will assign a separate number. Outcome number 1, outcome number 2, outcome number 3, and so on. And then encode it in binary and send that binary number. So is the revised scheme clear? Of the possible outcomes, we restrict attention to few, and we just say this will be outcome number 0, outcome number 1, outcome number 2, and so on. Okay. Now suppose you needed, you know, say 64 outcomes. Yeah. This set had 64 elements. Then how many bits will they have to transmit to identify a number? Number from 0 to 63 can be written in how many bits? 7 bits. Yeah. So then it will be, suppose it was 128, 6 or 7. Okay, doesn't matter. Yeah. Yeah. Suppose it was 128, 7. Yeah. So if this was of this cardinality, what would be the amount of communication they will have to do? Log of this. All right. So So this is the transmission cost, expected transmission cost with error delta. If you are working with n experiments and looking at the entire sequence, you assign it a code word. Yeah? Sorry, is this number making sense? Yeah. So these were n outcomes. Out of them, you identify some of them so that their probability is at least 1 minus delta. And then just assign them codes in some arbitrary way so that, and if anything, so let's call this number L, and if any outcome other than these special outcomes comes, Alice just sends the string 00000L, L times. Yeah. So the encoding, yeah. So now this is a fixed length encoding. The previous encoding, when we did that theorem there, different outcomes were being given, different length outcome. Here, everybody is going to be given. But if this something comes outside, Alice just sends all zeros. Okay. Bob thinks that it is something else, and he makes an error. But that error will happen only with probability corresponding to the outside, which is at most delta. Okay. So now, let me define this quantity. So now among the various sets here, which capture a probability of 1 minus delta, we try to find the smallest one. Yeah. So that they can achieve a probability of success of 1 minus delta with the minimum amount of communication. Yeah. And as n becomes larger, this number perhaps will become better and better. And the theorem, sometimes this is called Shannon's source coding theorem, is that limit as n tends to infinity, T delta n, for all delta. So if you take any source and consider strings of length n, and you try to capture a substantial amount of probability, no matter how you define your substantial, delta can be 0.5, delta can be 0.0001, delta can be 0.9, okay? This limit will always be the same, and it will be the entropy of the original source. Okay, so you can say the asymptotic optimum rate of transmission with vanishingly small amounts of error is actually the entropy. Yeah. So is this clear? Yeah. So instead of just thinking of a one-shot communication, Alice performs an experiment and in a hurry, she sends the outcome to Bob. Alice says, no, let me wait and collect n outcomes. And then this block of length n, I will encode. If that block of length n falls inside A, I will send the correct number of that outcome. If it falls outside, I will send 0. Bob sees this number and checks which outcome it corresponds to and decodes it. And he will be happy most of the time because this A has been designed so that it captures 1 minus delta of the probability. So yeah, so I hope now you have a sense of what entropy means and why. So if you have a source which is a probabilistic source, its entropy tells you the rate at which it grows. The source grows, yeah? Because, let me explain that a little better. It doesn't matter. Doesn't matter. Yeah, all my prefix code, Crafts inequality, etc., is useless if you are trying to do asymptotics. If you are doing asymptotics, all this nitpicking about prefix free, etc., are not important. You can just give them fixed length encoding. Okay, but you are allowing yourself small amount of error, whereas the previous one there was no error. It was perfect encoding. Yeah, if you do perfect encoding, then entropy up to +1, yeah, captures the amount of transmission. Yeah, but with variable length codes. But if you are insisting on fixed length, you can sacrifice a probability delta. And as you make n longer and longer, this delta can be made smaller and smaller, and you can still get away with, sorry, the quantifiers are opposite. You specify a delta. You say that I am willing to make an error of probability 0.00001. Based on that 0.00001, I will find an n, the right block length. And then Alice will start doing the experiments. She will wait for n experiments and then send some message to Bob. Bob will then decode and he will get all of them right. Yeah, he's not getting some right and some wrong. Either he gets all of them right or he's probably wrong, but maybe on all of them. But he will be right on all of them with probability 1 minus delta. Yeah. So this says that the source sort of can be compressed. See, initially you had n outcomes. Now, how many bits are being used? N times h of x. I mean, I'm putting an n here because I had divided by an n here. Okay. After I divide this number by n, I get h of x. So the actual number of bits I use is n times h of x. So for every n experiments I perform, I send these many bits. That means the source has been compressed at a rate of h of x per experiment. Okay, so that is the entropy. How much the outcomes can be compressed. Yeah, that when you try to express them in bits, that is the entropy of the source. Okay. Now, let me just make one more remark and then I'll stop. Yeah. So suppose this is the real line and you have a random variable which has some density function. Yeah, it takes a real value. So for example, yeah. So this is my random variable x. You can call it a source. Now, can we define a notion of entropy for this? Yeah. Now the point is, every single outcome has probability. When you have continuous random variable, every single outcome has probability 0. And 1 over, yeah. These things are pretty nasty when the denominator becomes 0. Yeah. And it's not even clear how to define entropy. And so we can fall back to our engineers' instincts and say, okay, we have this random variable, how are we going to transmit it? Okay. Now, if you want to transmit something, there are uncountably many possibilities here, and you want to encode it as zeros and ones. Yeah, it's not even clear how that notion of information, trying to capture information through transmission cost, is going to work. But you know, this picture still works. So let me try and explain. So suppose x1, x2, xn, these are n experiments, n IID draws of this x. Where do they live? In what space do they live? They live in an n-dimensional space. Yeah. So they give you a density in an n-dimensional space. So let me just draw 2 dimensions. So there was an x, which was a one-dimensional object. I drew IID, and then it gave me a density. Some parts were more dense, some parts were less dense, some parts were very rare, and so on. It gives you a density over R2 or Rn in general. Okay. Now, I would just like you to imagine, what would you like to do? Here we said we want to get the fewest strings, minimize the fewest strings so that their probability is at least 1 minus delta. Here, what would we do? In this space, we would like to identify a set A of the smallest. In discrete, we count. In continuous, we say volume. Yeah. So you have a random variable x, which is continuous, and now you consider its product distribution, IID. Yeah. And then you ask, what is the smallest volume that can capture 1 minus delta of the probability? And then, just for legacy reasons, we take the log of the volume, divide by n, because we are asking what is the amount of information per experiment. That's why we divide by n, and we ask, does this have a limit? What is its limit? Yeah, and the answer is the following. Limit n tends to infinity. We are trying to minimize over all sets A, which are subsets of Rn with probability of A, at least 1 minus delta. Maybe we divide by n and take log of the, what should I write here? Last time I wrote cardinality of A. What should I write here? We could think of this as the corresponding notion, because last time we were successful with this interpretation. It turns out that this quantity, so let us call this density. Yeah. So this is a random variable x whose density at little x is f of x. Yeah. Then this is the integral over all real numbers, yeah, of f of x log 1 over f of x dx. And this is called differential entropy. Okay. Yeah. So when dealing with continuous variables, you talk about differential entropy. When you deal with discrete random variables, you have your usual Shannon entropy. Okay? And what does it say? That as, yeah, one curiosity, sorry, that's beyond the line. Suppose my random variable is uniform in the interval 0 to half. Yes? So what is the density? What is this height? Sorry? 2. Yeah. Would you like me to compute the differential entropy of this X? This quantity, what is h of that? So each time the log of 1 upon 2, log of 1 upon 2 in base 2 minus 1, and you integrate from 0 to half of minus 1, and you get entropy is negative. Okay. Yeah. So the normal entropy, our entropy for discrete random variables is never negative. Yeah. But the differential entropy for continuous random variables can be negative. Yeah. Sorry, did I do it right? It's minus 1. Right? Sorry, getting tired. Yeah. Okay. So, all right. So let me just summarize what we did. We started with the problem of information transmission, and we tried to study that in the one-shot regime. And then we imposed on ourselves the restriction of prefix-free encoding. And prefix-free encoding had this nice Crafts inequality that gave us a formula. And that formula resulted in this theorem. Okay. Then we used this interpretation where we allowed ourselves a small amount of error. And then in the limit, asymptotically, the transmission cost corresponded exactly to entropy. Okay. There was a continuous analog of this, which tells us that as n becomes large and we move into higher and higher dimensions, your probability spreads over larger and larger volumes or smaller and smaller volumes. We don't know. Okay? Yeah. So the volume that is needed to capture a substantial part of the probability, okay, that also grows exponentially. But the exponentially with base what? Exponentially, there are everything is many things can be exponential, but we want to know what is the base of the exponent. So for that, what do? We take a log, and sorry, where is my definition? We take the log of the size and divide by n, so that I know the constant in front of n in the exponential, and that quantity is actually the entropy. So we are not trying to encode the entire space. Yeah. We are not even trying to encode not wholly or in full measure, but substantially. Okay. I don't know how many of you remember this. Shannon's paper was written in 1948. And in 1947, a speech was made in which these 3 words were made, not wholly or in full measure, but substantially. at the stroke of the midnight hour. Yeah, I don't know, but it's a coincidence. Thank you very much. Yeah, we'll meet again tomorrow. Questions? Yeah, please. Yeah, please.
So in the second scenario where you describe the situation where you allow a certain amount of error to occur, so practically how does that make sense? Because in our digital world,
So in an engineering setting, you're saying?
Yeah.
Yeah. So practically, so suppose you decide that, yeah, so there's some English text or some other text which is coming, and you take large blocks, okay? Now, suppose you say that I'm willing to live because my transmission anyway, it's a disk which I'm trying to transmit. It has only these many symbols anyway, yeah? So you first tune your parameter delta so that it is so small that you can live with it. That is, the chances that you will make an error within this, within that many gigabytes or something. Yeah, so the delta is much smaller than the number of gigabytes you're sending. And then you use block encoding so that it works for that. Now, many of these encodings in practical situations, they also have additional checks, okay? So those checks will tell you whether your transmission has failed or not. So Bob will again ask, and you might do something else to send slightly longer bits in order to get things done. Okay. The point is, most of the time, you would like to get away with a small amount of communication. But for our purposes, I think this should just be seen as an information measure in a probability distribution. How do we visualize it? Okay, and we visualize it through such pictures. That's all is the message for us today. It is not true that Shannon's theorems are used for data transmission, because here I've just said there exists a code. Yeah, you cannot scan through all possible outcomes and then try to assign codes. So in practical settings, other things are done. Okay. But even there, the tuning of parameters is done. You, depending on your rate of error that you can tolerate, you try to use strings of blocks of various lengths. This is the, you can say source coding theorem or source compression theorem. Yeah. So how much can you compress the source? No, it is related. So one can ask, so here, these xi's were arbitrary symbols. They are abstract symbols, abstract outcomes. Okay. Now, you could, these xi's could also have some weights. And then you could say, with some additional constraints, what is the minimum entropy or maximum entropy that you can achieve? Yeah. So it is the same formula, but you would write down some optimization problem with additional constraints. Now, those sort of constraints do not usually show up in this transmission business. Okay. Yeah, so that's a uniquely physics thing as far as I understand. So what are we going to do tomorrow? So the channel will start having errors tomorrow. Okay. And then we will ask, so while sending messages, Alice cannot trust the channel. Channel is going to send 0. You send in 0, but with some probability, it's going to send out 1. Okay. So how do you design codes so that you can exploit the channel in the best possible way? And there is a formula, not quite entropy, but mutual information, which will show up in the calculations. And that is what we will discuss tomorrow. The notes are here.